Thank you. So good afternoon. Today I'll be speaking to you about the subject of my thesis defense, which is Agile Multi-PHY wireless networking. So the large context of this thesis is industrial wireless networks. And in this context, the big question that we try to answer is how to build reliable wireless networks that have low power consumption. So when we speak about reliable wireless networks, we're looking at devices that are usually deployed in hard to reach areas. They're battery powered and they need wireless communications for all sorts of practical reasons within industrial plants. So they need low power consumptions and they need long range. So how do you build these kinds of networks? So throughout this thesis, we answer these questions on the physical layer, the MAC layer, and the routing layer. And one of the most important requirements is 5 nines of reliability, since they are used to monitor critical infrastructures. So the outline of the presentation would go as follows. First, I'm going to discuss the methodologies that we have used throughout the thesis. I'm going to discuss the trade-offs. Then we have 4 chapters, 4 sections, technical contributions. First, I'm going to discuss the trade-offs of between different physical layers for industrial IoT, and then I'll introduce generalized six-dish for Agile Multi-PHY wireless networking. Then I'll discuss how we use six-dish with heterogeneous slot durations and using 6-DIN amendment. Finally, introduce an objective function likelihood that we have developed for Ripple for multi-PHY routing to enable to improve the lifetime of the network. And finally, conclude with main conclusions in the future work. So within the market of industrial IoT, there has been a range of solutions. On one end, you have short-range technologies. These ones have on that end of the spectrum has the higher data rates. Examples of these is the O-QPSK 2.4 GHz physical layer, which is standardized by the IEEE, the 15.4 standard, and the 15.1 standard and the 2.4 gigahertz. One main limitation of this technology is that they are usually short in range. They are fit for, by short means, it's fit for small deployments within a building. However, routers are usually needed to bridge the gap between their gateway and the end devices. Some technologies that are based on these physical layers are the Bluetooth and the Zigbee for co-stacks. Therefore, they're used usually in mesh topologies. Now, on the other end of the spectrum, you have physical layers that are longer in range and lower in data rates. So they use a combination of slow bit rates and sub-gigahertz bands in order to achieve such long range. And therefore, that makes them suitable for urban area deployments. And usually they're deployed in star topologies because the end node can reach the gateway directly. And therefore, yeah. So, however, even these kinds of networks still require some kind of relaying. And to illustrate an example for this is our building in Milan. You have a LoRaWAN gateway here. And below there in the garage, in the parking lot, these sensors are unable to reach this gateway because of the different layers of concrete between. So 2 solutions here. One is to either have another extensive gateway or have a cheap relay to bridge the gap between the parking lot and the gateway. And different example networks based on that is LoRaWAN and Sigfox protocols. Now, recently there has been introduction of different chips that are able to provide different long range and short range radios within the same chip, which opens the question of how can we use, what is the potential of using these different physical layers within the same network now that they're available in one chip. Another element that has been introduced to serve the industrial IoT is the 6-dish protocol stack. It's based on the IETF standard. It's an IETF standard protocol stack. It's the IPv6 over time slotted channel hopping mode of the 802.15.4e MAC, which is basically a combination of TDMA and FDMA medium access control. Now, the way a network looks like in 6-dish is something like that. So you have, imagine we have this network here, which is 4 nodes in the root. For the network, the schedule is the time is divided into slots here, and at each slot, the mode can transmit, receive, or sleep. Within the 6-dish protocol stack, there are minimal cells that are allocated for broadcasts and network discovery. There are autonomous cells, which are used for link negotiations between different cells, between different nodes. And there are dedicated cells, which are used for transmission and reception for uplink of data packets. So the 6-dish protocol stack summarized more or less in this small table. It uses the data between the 4 physical layer, the short range, 2.4 gigahertz band, and it uses ripple at the routing layer. And the main 6-dish itself has a minimum scheduling function and 6 protocols to manage the schedules and the negotiations. Now, the vision of this thesis is not to try to find which physical layer is better than other in which scenarios and all this, but the vision is to introduce an architecture, an agile wireless architecture where we can enable dynamic trade-offs between range data rate and battery lifetime within the network. And therefore, this leaves us with 3 questions. First, is this multi-PHY integration interesting for latency, reliability, and battery lifetime, which are important KPIs for industrial IoT? Second, how to implement this in a standard protocol stack? And third, can this multi-PHY integration improve network time to first death? So hopefully throughout the thesis, throughout this presentation, we'll show how we answer these questions. Now I'll discuss the different methodologies that we used throughout the thesis. So first of all, we have relied on different physical layers that we have used throughout this thesis. The first one is the FSK with forward error correction in the sub-gigahertz band at 50 kilobits per second. So it's a slow bitrate option. Second is the O-QPSK modulation at the 2.4 gigahertz bands at 250 kilobits per second, which is a faster bitrate option. And third is the OFDM option 1, MCS3, the sub-gigahertz band at 800 kilobits per second, which is our fastest bitrate option. Now, throughout the thesis, we have followed different venues to conduct this work. So first, there was an analytical venue. In this analysis, we have designed a routing algorithm algorithm to optimize for network lifetime or time to first death for ripple. Second is simulation venue, in which we have developed a discrete event simulator for ripple to evaluate the performance of different objective functions how they improve the network lifetime in different random scenarios. And third, there is an experimentation venue that we have used quite thoroughly in the thesis, which is for the OpenTestbed, which is based on open mode these, which are open modes that combine both sub-gigahertz and 2.4 gigahertz bands and with different modulations and bit rates. And examples of these are in the box out there, so feel free to take a look. So now we discuss the first part, the first technical section, which is the trade-offs between the KPIs that are favored by different physical layers. So in this first section, we run that 6-dish protocol stack on top of different physical layers. So in order to do that, we introduce a PHY Agile radio interface to be used within 6-dish to be able to allow the firmware to choose at runtime which physical layer to use and which time slot template to use. To have a deterministic MAC such as 802.15.4e, you need a time slot template to be designed such that you have a perfectly synchronized, you have a well-synchronized network. And so usually with the classical 6-dish, it uses the O-QPSK 2.4 gigahertz band, and this is the time slot template for it. It shows a full transaction between transmission and receiving node, and it fits up to 20 milliseconds. So we have introduced 2 more time slot templates, one for FSK, which fits up to 40 milliseconds, and the other one for because it's a slow bitrate PHY, and the other one for OFDM, which fits up to 10 milliseconds because it's a fast bitrate escalator. And we run 6-stitch on top of each physical layer. Now, the OpenTestbed setup that we use to run these experiments is the one that is deployed at Inria-Paris. So the deployment looks like this with the different OpenTestbed boxes. The root is set somewhere here in the middle. And the Inria building in Paris, which you probably know already, it's a typical office building. And the implementation of that was done using OpenWSN reference architecture, reference implementation of 6-stitch. So first we look at the different performance criteria, the different key performance indicators that we have looked at for each of the networks. Now, the first thing we look at is the end-to-end reliability measured in PDR, end-to-end PDRs. And we see that the FSK network offered the 100% PDR followed by FDM and O-QPSK. Now, normally using a 6-stitch protocol stack, you should be able to get 100% PDR, irrespective of which physical layer you use. The reason to explain why we have this kind of PDR, we look at this plot below here, which shows the buffer occupancy in the network, in each of the networks. So it's a CDF of the buffer occupancy of each of the nodes in the network. And you see this right line here is the maximum buffer limit. So any node that passes this point will just drop an incoming packet. We see FSK has the best, has the lowest buffer occupancy compared to O-QPSK and FDM, which explains because of lack of relaying and lower retransmissions, which explains the table that we see above. The second element to look at is the end-to-end latency. In this element, you see we see that FSK again performs best compared to FDM and O-QPSK. And to explain that, we look at the time series plot of the whole experiment run. And we look at the latency, the end-to-end latency of each of the networks. The line here is the mean, and the range here, the first and third quartiles, and you see FSK has the best performance, again, because lack of relaying and lack of lower retransmission. Now, in the third aspect we look at is the battery lifetime, and you see that O-QPSK is offering the best battery lifetime. It's a very simple estimation, so a very rough estimation with battery lifetime. And to look at that in more detail, we look here at the duty cycles of the different radios, again in a time series plot in transmission, and you see that the O-QPSK and OFDM, essentially we see FSK, thanks to slower bitrate, has the highest duty cycle, and this is how it achieves the lowest lifetime. And this is in transmission, but Rx, which sees in performance. So the main outcome out of this is multi-PHY integration. This is the first question that we've been trying to answer for this section. Is multi-PHY integration interesting for these three KPIs? And the answer is yes, because each physical layer exercises different trade-offs between the different KPIs, and therefore it looks interesting to try to harness the advantages of each of the physical layers within one network. Now we look at the second question, which is how to integrate these different physical layers within one standard protocol stack. And for that, we introduced generalized 6-stitch protocol stack for Agile Multi-PHY networking wireless. So classically in 6-stitch, it has used time-slotted channel hopping over 16 channels of O-QPSK physical layer in the 2.4 GHz band. At the base of G6-stitch, we introduced time-slotted physical layer hopping for medium axis, and we defined it as following. For a mode, time is divided into slots, and in each time slot, the mode picks a physical layer that's independent from the one used in the previous slot. Physical layer here could be a combination of band, bitrate, etc. So the way this would look like is that these are our 3 time slot templates. And this is an example of the different of a slot frame. So at each slot frame, a whole different time slot template is used, and a whole even a different radio driver, obviously, if we have different chips. So this has been developed based on the OpenWSN reference implementation of 6-fish. It took the 5K lines of code, 80 plus files have been affected, including some refactoring to be able to achieve that. Now we explain, I go over a very quick overview of the mechanics of G6-fish for post-stack. So imagine that we have this network, again, 3 modes and a gateway. So the first phase that the node goes into, the network goes into, is the discovery phase. In this, the first thing that happens is that the root is set, and it keeps broadcasting the information using enhanced beacons on one minimal cell per each physical layer. Then it also allocates an autonomous cell for itself to be able to receive link negotiation requests using the longest range physical layer, which in this case is the FSK. Now the location, the place or the location of this autonomous cell is in the schedule is determined by the minimum scheduling function, which is basically a hash of the cell EUI against the slot frame length and the channel template length. Now all modes are listening over the longest range physical layer, in this case FSK, until D hears or they basically hear the first beacon over FSK, and then B, which heard in this case, just for example, B heard first, so it extracts the information of the different minimal cells from the enhanced beacon, and then it populates its own schedule with the beacons with the respective minimal cell, and that allocates for itself autonomous cell and the rest, and the same case for the rest of the modes. Now, after a while, modes are discovering each other on the different minimal cells over different physical layers, and they start populating their neighbor tables. In this case, the neighbor table is a combination of the EUI address and the physical layer that's used to communicate with that neighbor. Now, let's say after a while, modes have discovered each other, and they have, or at least they discovered some neighbors. Then the network goes to a second phase. Well, at least some of these modes would go to the second phase of parent selection. For the wrapping layer, where we do the parent selection, we show that we extend the MRHOF, or minimum rank with hysteresis objective function, with a very simple extension. And MRHOF is based on ETX, so we just multiply this the ETX of a link by a factor for each physical layer, and the factor is 1 for the fastest bitrate, which is OFDM, followed by 2 for O-QPSK, followed by 5 for FSK, and this way the lowest bitrate is least favorable, and the highest bitrate radio is most favorable. Now let's say that mode B runs its own objective function at triple, and then it decides that mode A is the best route for uplink is a direct link to A using OFDM physical layer. So what happens is that mode B starts the link negotiation process. So what does it do is that what it does is that it allocates, it sends a 6-stop request for A, specifying the number, the physical layer that's it's using to this cell, and giving it some options for cell locations and channel templates. And channels to use, which are determined by the MSF. Now, let's say mode A, the root agrees. They both allocate a dedicated link using both EM in this particular slot. And therefore, same thing happens with C, and it picks, we assume here that the routing function picked A, picked the O-QPSK link to D, and D decides that it wants an FSK link directly to the root. So the resulting schedule would look something like that, more or less, or basically it would look something like that. And this is, as we see that it's a process that's ongoing as the network is running. It keeps discovering new neighbors, picking new parents, negotiating new links. Now we look at the performance of G6 compared to different single PHY networks. So the first thing we look at is the network formation time, the first key performance indicator. And this is a time that's taken for the root to get the first packet from all the modes in the network. So the first thing we look at is the network formation time, and we look at the CDF of the nodes, and when they send their first packets in the network. And you see that G6 in red here has the fastest, almost the fastest compared to FSK. It has the fastest network formation time compared to the rest of the physical layer. And to understand why it does that, we look at an illustration, which we're zooming in basically on G6. So what we see here in the next, in this plot, is a breakdown of the different physical layers used for routing as the G6 network is forming. So what you see that at the beginning, G6 explores different FSK links, which struggle a little bit because they have long range, there's a lot of contention on the minimal cells. And then it explores more O-QPSK links because they're short range, less contention. And then OFDM struggles a little bit to go up because it's broadcasting over 5 channels only. So again, more collision. However, because it's able to see all these nodes at the same time, it explores all these different physical layers. This is why it's able to go faster than any single physical layer network. Now we look at the latency performance of G6 and compared to different physical layers, and we see here this is a time series plot of the latency of both the 4 networks, and you see the G6 in red performs the best latency compared to the others. And essentially, it's because it's able to in a G6 network, the node has far more neighbors than any other single PHY network, and therefore it's able to pick the best PHY for routing. The third thing we look at is the reliability of the PDR of the network. And we see that the G6 has 100% end-to-end reliability compared to FSK and OFDM. This is actually quite interesting because we're looking at this. If we look at the steady state performance of G6 when it's stable, we see that it's only 20% FSK and 30% of O-QPSK links. Even with that, it's able to have 100% reliability. Finally, we look at the last KPI, which is grid duty cycle or battery lifetime of the network, basically. So first, you see that this is the same time series plot for the duty cycles of different networks. And we see that G6 has was able to improve the performance, was able to reduce the duty cycle, the overall duty cycle of this network compared to FSK. Again, while maintaining 100% reliability. And to see how it's able to achieve that, we zoom in into this duty cycle and we look at the duty cycle breakdown of the different physical layers of G6. So we see that as the network is forming beyond this point, like 15 minutes into the network, the FSK duty cycle starts to decrease because the ripple objective function favors faster bit rates. And you see that the OFDM, which is the most favorable physical layer for ripple, the duty cycle starts to increase a little bit there. And this is basically what offsets this gap in duty cycle, and therefore this is how it's able to improve its duty cycle performance compared to FSK. Now we combine these two with these duty cycle measurements, and we have try to have a very rough estimate of the battery lifetime using a very simple model. And you see here that the G6 network in red has a better lifetime than FSK. and there's still the time to first death is still the same, but generally this shows a room for improvement for improving time to first death, which is what we explored in the last chapter. So now we'll look at how can we use G6-ish with heterogeneous slot durations. So far we have used the longest slot duration for the different physical layers. This leads to basically wasting time, because you're wasting the time for the long 40 millisecond slot if you have a physical layer that takes just 10 milliseconds. So a more complete approach would be to vary the slot duration on a slot by slot basis based on the phi used. And we show how we're able to do that using the same G6-ish protocol amendments. So again, these are the way this looks like is that, again, these are our slot templates. And here you see OFDM takes only a slot of 10 milliseconds. O-QPSK takes a slot group of 2 slots, taking 20 milliseconds, and FSK takes 4 slots, a group of 4 slots, which takes 40 milliseconds. So to give an idea of how this would look like, so imagine that we have this network again, and on the x-axis we see our slot template, our slot frame length, which is 163 slots of 10 millisecond slots. On the y-axis, you see the hopping happening over. We see different physical layers, or the hopping scheme for the different physical layers used in the network. There's 16 channels of O-QPSK, the 2.4 gigahertz band, there's 2 megahertz channel bandwidth, 16 channels for FSK, the sub-gigahertz band with 200 kilohertz bandwidth, and 5 channels for OFDM with 1.2 megahertz bandwidth. And in the minimal cells, you see the O-QPSK minimal cells are occupying slot group of 2, FSK occupying a slot group of 4, and OFDM minimal cell is just occupying 1 slot. And you see the autonomous cells of each cell of each node is allocated using slot groups of 4, and the dedicated lengths for FDM and FSK and O-QPSK are allocated with 1, 4, and 2 slots. One amendment that we have done to be able to achieve that is to additional amendment, which is to modify the slot reservation scheme such that it can detect overlaps or partial overlaps between the different slot groups, which led to further interesting questions, but they're outside of the scope of this thesis. So the implementation of that looks like that. So this is the same thing. This is the same capture. This is a logical analyzer capture showing the interaction of the protocol stack between 4 modes. And for each mode, we capture the slot duration, the transition between the slots and the MAC activities. And this basically reflects the very same plot that you saw in the previous slides. So far, we have answered 2 questions. First, is multi-PHY integration interesting for latency, reliability, and battery lifetime? And the answer is yes, because of the different trade-offs that exercised by the different physical layers. Second, how to implement this in a standard protocol stack, and for that we have introduced G6 and 16. Now the question that we answer next is, how does this improve the network time to first death, or the time to first death of the network? First, I'll need to explain a little bit why time to first death. So, one practical aspect of many industrial deployments is that the major cost element of changing batteries is not actually the price of the batteries, but the price of sending someone to deploy the batteries. And the price of the battery is actually negligible, becomes negligible compared to the cost of sending that person. And in this case, if one mode dies, then it makes more sense to change all the batteries in the network, regardless of how well they're performing. So this opens the question of how can I achieve some kind of load balancing in the network such that we postpone the time to first death as much as we can. So for that, we discuss our last technical section, which is an objective function, which we call LifeOF, that we have developed for multi-PHY routing and Ripple to improve network lifetime. So now we give a bit of an overview of LifeOF. So it's meant to be integrated within Ripple, a distance vector routing protocol. And we have evaluated that in RippleSim, which is a discrete manipulator we developed particularly for that particular purpose. And it uses dynamically calculated metrics to achieve this optimization objective. So using LifeOF, normally, in a very normal general case, a node picks between two modes of connectivity. So the first, it picks a short-range PHY to save its own energy, and then it picks a long, or it picks a long-range PHY to avoid relaying and consuming more of its own battery, and it keeps picking the best routes accordingly until it reaches the first death in the network. So a logical sort of block diagram or overview of LifeOF is illustrated here. So basically, to achieve that, we have three components running. One component is node remaining lifetime evaluation. It keeps evaluating the remaining the lifetime of the node. Another component is path evaluation and selection. It keeps evaluating the different paths and selects the best one. And another component that keeps updating the ranks, either when there's new lifetime or a new path has been selected. So, okay. So, just to give an overview again, a more detailed overview of how LifeOF works. So the objective really is can be summarized in three main elements. The first element is to select the path with the highest lifetime. So let's assume that A is picking the best, is trying to route its traffic. So now there are two paths. One path has all full batteries. Another path has has one of the batteries not full, and therefore this path with a higher lifetime is favored. Another element is that let's assume the node has both lifetimes. The different paths have the same lifetime. Then it tries to select the path with low power consuming physical layer. So this you see here that it's uplinking using this physical layer to this neighbor, which is more power consuming, either because of higher ETX or higher power consumption of that physical layer. Then this path is stable. Now let's say both paths have the same lifetime and the same power consumption of the uplink physical layer. Then the one with the minimum hops is used. And to achieve this in Ripple, these properties are expressed within some kind of rank, an expression of rank, which we show here. It basically shows, like three main components, which is the lifetime of the path, which is the minimum lifetime of the path here, the weighted ETX of each physical layer, which is the combination of the ETX of the layer of that link and the power consumption of the link, and the hop count of the path. Now we look at the performance analysis of LifeOF, and we compare that with IETF standard MRHOF. Now, MRHOF is an ETX-based objective function, and we compare against MRHOF, even though it does not optimize for this purpose, because we want to show that at least we improve the network lifetime. Because imagine if we introduce this function, we still have the same lifetime as MRHOF, then it's senseless. So that's why we compare against MRHOF. So first we look at one example or one scenario This is a topology that's randomly generated topology. One of the randomly generated topologies for our simulations. And the first one, we apply MRHOF, and both topologies are supplied with the three different physical layers, the O-QPSK, ODM, and TSCH. Since MRHOF optimizes only for latency, then you can see that it ends up picking FSK lengths. LiFi-F, however, is able to combine the faster bitrate PHYs in order to improve the network lifetime. What's happening more specifically in LiFi-F is that at each epoch in the simulation, it actually alternates, it finds better topologies, or finds different topologies to try to load balance its traffic. And to demonstrate that, we look at this diagram right there. And this one shows the simulation during on the x-axis, you see the simulated years network run. On the y-axis, you see the estimated lifetime or time to first death at each epoch. So you see first, this in blue here, this is MRHOF. It converges on some kind of topology at the beginning, and then keeps fixed on that until it reaches its first death at nearly 1 year. LiFi-F starts with some suboptimal topology. It's not far actually from MRHOF, but then it finds a better topology, and then it boosts its lifetime, its expected time lifetime in the first epoch, and then starts gradually dying until it reaches its first death at 3 years. Now we look at the distributions of the time to first death measurements of each of the networks, of each of the scenarios that we have run throughout this section. So we have run 4 different scenarios. One is using MRHOF with only a single physical layer of FSK. Another scenario was using MRHOF using FSK, O-QPSK, and ODM, the multi-PHY scenarios. And one using LiFi-F with FSK only, single physical layer network. And one using LiFi-F using FSK, O-QPSK, and ODM in a multi-PHY network. So for each scenario, run 50 different runs, pseudo-randomly simulated runs, 100 nodes in a 2x2 square kilometers area. So we see in both scenarios of MRHOF, in the single physical layer and the multi-physical layer, it basically it has basically the same performance because it picks FSK anyway. It's the best performance, the best PHY in terms of FSK, so why pick faster links? When we introduce when you use LiFi-F only with a physical layer, it's able still to improve the network lifetime, even though it's only using FSK, because of its load balancing feature. And we see that the center of the distribution of time to first death of each of the runs reaches up to nearly 2.4 years. Now, finally, we look at the LiFi-F performance with multi-physical layers, and we see that it's able, thanks to its ability to integrate faster bit rates PHYs, then it's able to even push the time to first death even further, up to 2.8 years, like the center of distribution here. So, to conclude at this point, the vision of this thesis have been Agile Multi-PHY wireless networking. Does it make sense? And we summarize that in 3 questions. The first question is multi-PHY integration interesting for latency, reliability, and battery lifetime? And the answer is yes, because naturally every physical layer focuses on different key performance indicators and favors that. So it's interesting to harness the different advantages of the different physical layers. And we showed that in the first section. Second is how to implement this in a standard protocol stack, and we demonstrated that in G6 and 6DIN. Finally, can this improve network life time to first death? And for that, we introduced the multi-PHY live wave for multi-PHY routing in RPL. And we showed there how our objective function can adapt the network topology at each epoch, different epochs, to load balance its traffic. Now, future work can be done, different paths for future work can be done based on the thesis. First thing is that could be interesting is applications of what are more applications of time-slotted physical layer hopping, especially in link robustness. And there's already existing work on that, work already by Professor Jabi on improving, using modulation diversity to improve link robustness. Second question is, or second venue would be, how can we improve, what can multi-PHY integration bring to multi-PHY gateways and probably even multi-PHY cellular networks, especially with the case of with the problems of mobility. Third, what can multi-PHY integration bring as opportunities or challenges for security, especially in multi-PHY architectures? Fourth, how can we introduce routing metrics to improve the network budget, network operational costs? And this, for instance, we have on the routing aspect, now that we have looked at time to first death, maybe we could have a more comprehensive view of what's the total cost of running a certain link, and does it make sense to use that link or not? And there are all sorts of metrics that have been introduced for RPL to express different features, different properties of the link. So how can we make use of that for more economic aware operation of the network? And finally, what can this bring to long-range wireless networks that can reach up to 100+ kilometers? And last week, with our Inria team, we have built a network that reached 100+ kilometers, 100 kilometers. So using low power devices, using basically open node Ds. So what can this bring to last mile coverage, or more than last mile, last 100 kilometers coverage? So these are the actual modes. So finally, the thesis has resulted in 4 different papers. One of them is still under review, and 3 different software contributions to one, for example, for the UC Berkeley OpenWSN project, the OpenTestbed project, and discrete event simulator. And as I just mentioned, the network that we have built, just the small demonstrations to show the potential of long-range mesh networking. And using these devices, basically, we were able to build 100 kilometers link using just these devices and 2 cars. And it was in the south of Paris, reaching from Paris way beyond Orient. So thank you.